Okay, good afternoon, everybody. It's a pleasure for me to introduce Roy Overbeek, who is the speaker of this afternoon seminar in the GReTA series of seminars. Roy will speak, as you can see from the title, about the PBPO plus approach, presenting it as a unifying theory for quasitoposes. Please, Roy, the floor is yours.
Thanks, Andrea, for the introduction. And also thanks to the organizers of the GReTA seminar for allowing me to speak here. Yeah, I would just like to mention that the content of this talk is joint work with Jörg Endrullis and Aloïs Rosset, who will also be in the discussion afterwards, I think. So I can summarize the content of this talk in one slide. Let's say one rewriting framework is modeled by another. If for every F rule you can find a G rule, such that they generate exactly the same rewrite relation. So we really want equality of the rewrite relations, not inclusion, as you sometimes find in the literature. And then the main result of this talk is that in any quasitopos using regular monic matches M, we have these three relations. So recall that the regular mono is a mono that is an equalizer, but we will not explicitly use this property anywhere. And you can extend this result by something that's stated more generally already in the literature, in the agree paper, by this relation over here. So we really have a nice subsumption of kind of three otherwise incomparable chains of rewriting formalisms. And the reason that we focus on these specifically is that we were interested in something like PBPO plus for our own reasons. That's what we landed on. And very similar to that are agree and PBPO, both by Corradini and others. I'll explain in more detail later what they are. And then, of course, DPO and SqPO are both historically quite significant, so they are nice to include in this picture. With this talk, there is an associated paper. It's available on arXiv if you want to take a look at it. And if you have comments, it will still be relevant for us because it's currently under review at the journal. It's an extended version of a conference paper previously presented at ICGT. So that's where you might have seen PBPO plus before. And so the content of this talk is, I will try to keep it fairly generally accessible. So if you know DPO and you know some flavors of adhesivity, I hope you'll be able to follow this talk. I will first talk quite generally about the notion of a quasitopos because I think it might be of interest to the rewriting community in general. And I will just mention the properties that we use that hold in a quasitopos. Then I'll explain PBPO and PBPO plus. And then I'll go through the three modeling proofs in some detail to show you exactly how these quasitopos properties are leveraged here. So, okay, let's start with the quasitoposes. Here are two standard definitions. Yeah, a topos captures kind of the notion of a set-like category. So often structured sets turn out to be toposes. And these citations here are just standard references. This is the Elephant by Johnstone, and these are the lecture notes by Weiler. And the main difference here is that in a topos you have a subobject classifier, and in a quasitopos you only have a regular subobject classifier, so only a classifier for the regular monos. And we will actually not use these properties very explicitly. Instead, we rely on consequences, a number of properties that hold for quasitoposes, and a nice summary you can find in this paper of Baron and colleagues that was presented at ICGT last year. I think they took some time to scaffold all that together, so we were quite happy that we were able to make use of that. So now I will just go, I will show some examples of, talk a bit about examples of quasitoposes, and then I'll go through the properties that we use. So of course, any topos is a quasitopos, and these already include many graph-like structures of interest. But then there are other examples that are not toposes, the canonical one often being the category of simple graphs, so you don't have the parallel edges. This paper by Johnstone, Leck, and Sobocinski, they prove a general principle for showing that something is a quasitopos, and then these are some of the examples that fall out of it. But there are also other examples that may not even seem directly relevant for graph rewriting. One of them is an infinitely distributed complete lattice. I will just say IDCL. So complete lattice is a partial order where you have all the joins and meets. And infinitely distributive just means that the meets disjoins, the meet distributes over the joins and vice versa. And then in the literature, you also find this notion of an L-fuzzy set. These are it's just a category of sets with the usual functions, except that the elements of the set have a value associated with them from a partial, well, from a complete lattice L. So the idea is that for every element, you have a sort of indication or degree of set membership, and the functions then are required to be increasing with respect to this order. And this was quite, judging on the volume of literature on this, it seemed to be a fairly popular topic for fuzzy logic. I'm not sure what the status is these days. But we had a particular interest in this because last year, for the conference paper associated with this talk, we already defined this notion of graph less equal, as we called it, where the objects are graphs labeled from some complete lattice L, and the morphisms are graph premorphisms that respect the order. And back then, we didn't know about this connection with the L-fuzzy sets, but we could call them L-fuzzy graphs. And we use that for implementing a kind of relabeling mechanism for graphs. And in the paper at GZM, we used it for showing that left linear term rewriting can be embedded in some way into graph rewriting in a way that preserves termination. So there's some interesting applications of this. And also for this, we wondered if it is a quasitopos. And it's mainly Aloïs Rosset that looked into this. And he has some proof now about L-fuzzy presheaves being a quasitopos if L is an IDCL. It's currently in the draft stage, so you can expect it in the future at some point. But so I just want to say this because it's maybe another interesting addition for the list of quasitoposes, and it also shows that there might still be plenty of categories out there that fit this mold that we can discover. But I will not talk about this in the rest of the paper. So let's go to some of the properties then. And I'll start with the exactness properties, so which, well, we know all limits exist, but how do they, and co-limits, how do they interact? And as is well known, any topos is a quasitopos. And any topos is adhesive, where I will just show the part of the definition that I would like to emphasize and compare. So adhesivity tells us, well, pushouts along monos are van Kampen, meaning that when you have pullbacks in the back, then the front is the top is a pushout if and only if the pullbacks are, the fronts are pullbacks. And at some point then this notion was weakened for, at first it was called quasi-adhesivity. It was thought that this would capture the notion of the exactness properties for quasitopos, I think. So then you just have this van Kampen property along the regular monos, indicated by the hook. But it turned out that this doesn't hold generally. You need an additional condition for the quasitopos, namely that regular subobjects are closed under binary union. In effect, the quasitopos is quasi-adhesive if and only if this property holds. So we need some weakening of this. And then in the literature, you find this notion of Rn quasi-adhesivity. And then the point is that you no longer have the Van Kampen property, where you have this equivalence between the top and the front. You just get it in one direction. So if you have pullbacks all around, you will have a push-out on top. So it's basically just stability of push-outs on the pullback for push-outs along regular monos. But there's of course another way to weaken quasi-adhesivity, which is to keep the Van Kampen property, but now require the cube to have monos on the verticals. And people who use DPO will use this type of category a lot. And specifically for M, the regular monos, then it looks like this. And then through the notion of partial adhesivity, you can show that a quasitopos is also M-adhesive for the regular monos. So we don't just get this stability of push-outs on the pullback for regular monos, but in a special case where these verticals are regular, we also get the Van Kampen property there. And of course, in all these categories, push-outs along regular monos are pullbacks, and we will also use that in our proof. And there's one more property, namely that push-outs are stable under, that regular monos are stable on the push-out. This also holds in a quasitopos. Now, we can also say something about the monomorphism classes in the quasitopos. So recall that the monomorphism is extremal if whenever you factor it as an epi followed by some morphism, you can conclude that this epi is an isomorphism. And we have in general categories this chain of implications. So a regular monomorphism is strong, etc., where we don't need to know the definition of a strong monomorphism. And that, as is well known then for a topos, every monomorphism is regular, so these all coincide. But for a quasitopos, we still have the nice property that the extremal and the regular monomorphisms coincide. And from this then, you get nice decomposition and composition properties. So if the composition is regular, you can conclude that the first factor is regular, just like for the generic monomorphisms. And also it's stable under composition, which neither of these hold in general categories. What else do we have? Any morphism F can be uniquely factored in a quasitopos. So there are two factorization systems. One is you can factor it as an epi followed by a regular mono. The other is you can factor it as a regular epi followed by a mono. And we will actually use the first one. Of course, this is up to isomorphism in C. And also unrelated to that, if we have a quasitopos, we take a slice category over some object in this quasitopos, then we have another quasitopos, quite similar to what we have for toposes. Then a very crucial property for our purposes is that partial maps are represented. So I will just explain what it means in set. Let's say you have this partial map which multiplies elements by 2. So in this case, in the domain, we only have 1 and 5, 3 and 7 are not part of it. Then this partial map we can represent as a span where this monomorphism picks out the domain and the F does the multiplication on the domain. And now in set, we have a third possibility, namely we represent undefined in the codomain. So we add a bottom element. And then we can represent the partial map as a total map like this, where we send 3 and 7 to the bottom element. Now, how do you define this arrow categorically? Well, in this case, it's the unique arrow that makes this square a pullback square. So uniqueness follows that we have just one choice where to send the undefined elements. And you can then, I mean, it's sometimes taken as a definition, but it also follows from the other definition that we saw. In a quasitopos, then you have for every object A, you have this classifier with a classifying object, such that for every span as depicted, there's a unique morphism that makes it a pullback square. So you can find it in the standard literature on quasitoposes, but also the agreed paper is very useful in understanding how this works, in particular because it's the first paper that introduces it to the graph setting and investigates its applications. So what does this look like in graph? Let's say you have a graph which just consists of two nodes with an edge between them. Then, of course, in the classifying object, it includes A. And now for any nodes that are not part of a partial map into A, we need to have an undefined element, so a bottom element. And then for any edges that are not part of a partial map into A, we need to be able to, I mean, they can go between any of these two nodes. So we need to have a kind of a type edge there, which can uniquely capture those edges. And these kinds of examples, like I said, are it's very nicely explained in the agreed paper from 2015. And then I would just like to mention that we can also just classify regular monomorphisms, not just spans, because this triangle over here, we can expand to this square right here where we have an identity on top. And this just means basically that anything that's not in M gets wrapped around into the type graph. Then there's one more property, this notion of RM materialization. I will get back to that later because it will be easier to explain and motivate after I've introduced PBPO and PBPO plus. So stay tuned for that. So let me explain PBPO and PBPO plus. As a shorthand, PBPO plus is a shorthand for PBPO by Corradini and others with a strong matching requirement. So PBPO stands for Pullback-Pushout approach, was first introduced in 2017, extended version in 2019. Then last year we proposed PBPO plus, and now we have this preprint for which I'm doing the talk. And well, what's a rule? What's it like? It's a diagram of the form depicted here. On the top, we have a span of patterns, just like in DPO. And on the bottom, then we have now a span of type graphs. And vertically, we have typings for each respective pattern. And the rule is said to be in canonical form if this left square is a pullback and the right square is a push-out. And already in the original paper, they show that every PBPO rule is equivalent to some canonical PBPO rule. So we can restrict attention to that. And a PBPO plus rule, it's basically you take a canonical PBPO rule. Technically we leave out the push-out here because we can construct it. And then we also require that the TL is monic, which will imply that the TK is monic. We do this just because we find the rules easier to understand that way semantically, but there's also a technical reason why you would prefer this probably whenever you apply strong matching. Okay, how is a PBPO step performed? We start with just outlining the rule like this. And the step then from GL-GR is constructed as follows. We try to find a match of L, an occurrence of L in GL, a host graph, just like in DPO. But now also we like to have what we then call an adherence morphism, which shows that GL can be typed according to L prime in a way that's compatible with this TL morphism. And now, applying a pullback here, you can do like deletion operations and cloning with filtering operations. And doing another pullback, you can restrict this to the pattern part here. And then when you do you can do a push out over here, which will allow you to merge elements and add new elements, just like in DPO. And you can do another push out here to fill out the diagram in this fashion. Now for PBPO plus, what's then the difference? We require then that this triangle is a strong match, as depicted here. So the idea is that the occurrence M of L in GL, if this is a pullback, it means that only the M of L is mapped onto the TL of L and nothing else. So that kind of means that the context cannot be mapped onto the pattern. I will show an example in a short moment. And moreover, because TL is monic by definition, we know that in any category, M, decay, and U are also monic by pullback stability. But otherwise, they are the same. So that explains why we chose not to introduce another name, but rather just show that this is a modification of PBPO. So what are some features? I'll give a short example a bit later, but this L prime essentially allows you to model some sort of notion of an application condition, because if you choose something very restrictive here, that limits the matches that you're allowed to use. And then, the pullback deletes and clones, and the push out merge and adds elements. So it's quite powerful. Let me first motivate strong matching through a simple example. So on the top here, we see 3 patterns, and what we want to do is, from some node X, we want to delete a loop that it has. And if you look at the type graph L prime, we see we have a kind of sync node for the context. And we don't have any other edges going from this X to the Y, and no additional loops on this X, which indicates that we would like to exclude such graphs that have these properties. So here is an example of a strong match, where only this occurrence M of L is mapped onto this TL of L, and these Y nodes are all nicely mapped into the Y sync node. So we have a nice separation of the pattern and the context. And then you apply the pullback over here, and then the push out. The push out doesn't do anything in this case, but you see that indeed only this loop from this single node is deleted. Now in PBPO, if you don't control the matches M and the adherences alpha, then this is also a valid rewrite step, where we, because we have a commutation requirement, we basically map all of these nodes onto the pattern part here in L prime. And then when we do the deletion, in this case, all the edges would be deleted. So if you use PBPO like a kind of macro, for instance, you can just choose not to use adherences like these. And then with TL non-monic, you have some flexibility in how you define L prime, which can be nice. But if you think about generating a language, we think that usually you would want to use strong matching. That's all I want to say about that. And here then is a slightly more complicated example. So if you look on the bottom here, we're trying to split this node into 2. We're deleting some of these type edges, let's say. Later on, we're adding a loop and some new node. And also we're forbidding certain connections. So we don't want any edges from the context to the Y node, for instance. So this is a valid strong match. And then when we do the pullback, you see, for instance, that this edge from Y to the context is deleted. when we do the splitting here. And then when we do the push out, well, you get the result that that one would expect, as schematically depicted in the bottom. And just for some historical note, why did we care about PPO plus? It's because we cared about operations of this form. We first proposed some set theoretic formalism for graphs specifically at ICGT 20, and then we tried to categorify that one, and it doesn't correspond exactly to PGR, but it's very close. And so one feature that you can do in particular that we also studied here was the ability to take like edges that lie on the pattern but are not part of it. You can, for instance, just flip them. If you look at these graphs, if you just squint your eyes and up to isomorphism, this is something that you can do. So in that sense, it's quite powerful. Okay, then I want to discuss the modeling results, starting with PBPO. And then I'll first mention this other quasitopos property that I promised to you. Now, if we want to find, if we want to model PPO rules, the PPO rule does not use strong matching, so we should be able to find a PPO plus rule that kind of does the same thing or allows the same thing, but then using strong matches. So let's say right now for just generic monos, not regular ones, let's say we are given some typing TL, think of it as given by a PPO rule, and then a match and adherence as depicted. What we would like to construct is a PPO plus typing TL prime, and by definition we need it to be monic, such that ideally with the same match, we can make a strong match down here. And we would like to correspond in some sense to the original match and adherence so that we don't get an over approximation. And this commuting triangle gives us that. And for the conference paper, we mulled over this property a long time, tried to find it. And at some point we realized it existed in the literature in quite a different setting. This is about static analysis, essentially. And it's a notion of materialization. So the idea is that if a category admits materializations, it means that for any morphism, such as the TL, you can find a terminal factorization that is a mono followed by some morphism, meaning that, for instance, for this M and then alpha, we can find a beta into the terminal factorization such that this square is a pullback and this triangle commutes. And in that paper, they show that materializations exist in toposes. So that's almost what we want. And I should say, for the conference paper, we had this subsumption result of PPO for toposes, and then we also used this property. But now for the generalization, then we are dealing with regular monos. And so in this paper, we show that you have something like RM materialization, where now the monos are regular, as well with the result that these exist in quasitoposes. And how does this work? How does this come about? This proof is a fairly straightforward adaptation of the original proof. The idea is that if you're in a topos or a quasitopos, it's stable on the slicing. So if you go to the slice category over L prime, this TL will be an object there. And if you then take the classifier, the classifying object for this TL, it's exactly this B prime morphism over here. And this arrow over here will be the classifier, the injection into the classifier. And then you just have to switch perspectives to show that you get this on the original category. It's quite an interesting proof, I thought. Okay, so having said that, we can get to our theorem. Let's say we have a category that is a quasitopos. The statement here is more general than what I said before. It says that for any rule row, we can find a class of rules, PBPO plus rules, that collectively model that row rule. Note that there's no assumption yet about regular monic matching. When you add that, as I will show, we get what we wanted, namely that there's a single rule that models it. But this is the general statement for that. And instead of just dumping the definition of this compact row on you, I will instead show the proof sketch, and then it hopefully will be clear which rules you should put into that set or class. So, okay, we are given a PBPO step diagram as depicted. And what we can do is, well, we can tuck the morphisms to the side, but because we're in a quasitopos, we can factor M into an epi followed by a regular monomorphism. And we can then define F as the composition of M prime and then alpha. And note that here we have a regular monomorphism factorization of F. So now, because we can materialize F in quasitopos, we get these two morphisms. And because it's terminal, by the materialization property, we get this beta down here. It's unique. We don't necessarily need uniqueness, but we get that it's unique, such that this triangle over here commutes. And more importantly, this triangle over here is a pullback. And now, starting from the bottom here, we can do pullbacks all the way up, and then here push-outs all the way down. And with reasoning, using the pullback lemma, you can show that the diagram nicely splits like this. And now we find hiding here a PBPO plus rule, because we have a monic TL here, the F prime, and even with a monic match here. And it generates a step from GL to GR as well. So from this picture, then, what do we need to put in this compact set? Well, for this particular factorization TL of E and then F, we need to add this. So we need to consider all factorizations of this form. And now, if you would have a lot of isomorphic rules. So if you just whittle down to the rules that are not isomorphic for some suitable notion of equivalence, then, for instance, in finite graphs, there will of course only be finitely many interesting epimorphisms, so that the class is typically just a finite set of rules. But note that in particular, if TL is a regular mono, it's extremal. And this E is part of a factorization of TL, so that would imply that the E is an isomorphism. And similarly, if the M is a regular mono, then likewise it follows that E is an isomorphism, which means that TL and F are, treating this as equality, are just the same morphism. So that's how we arrive at this result that if you're in a quasitopos and matches are regular monic, or the TL of rho, the PBPO rule, is regular monic, then there's a single PBPO plus rule that models it, and the proof provides the construction of it. All right, then let's move on to agree. It was first proposed in 2015 at ICGT, and later there's an extended journal paper for it. So note in particular that this predates PBPO by a few years, and of course also PBPO plus then. And agree is defined for a category which has M partial map classifiers for stable system of monics M. In the quasitopos, then we have this for M, the regular monos. And an agree rewrite rule is of the following form. So it's like a PBPO plus rule, but we don't have this corner over here. We just have the typing for the K prime. Now, a rewrite step then is a diagram of this form. Again, it looks very much like a PBPO plus step. The only difference is that here, what before was the TL and the L prime and the L prime morphism, they are fixed by the rule. So in that sense, we can also think of PPO plus as agree, but bring your own classifier. So these three rewriting formalisms are all very closely related. We might as well have named it after agree from this perspective. And then because of this approximation, it should be no surprise that when you're in a category satisfying the conditions of agree, for instance, a quasitopos, then this rule depicted here models the agree rule. So what you just do is the classifier provided by agree, you now just make part of the rule. So yeah, we get as a corollary that we have this relation here. And this proposition is very similar to one stated in the PPO papers, or maybe just the journal paper, I don't recall at this moment. Also for this rule, they state this equivalence, but note then that you have to fix the adherence to be the arrow induced by the partial map classifier, because by definition of a PPO rule, you're also allowed to pick those morphisms that do some collapsing, and then you have a larger rewrite relation. So in graph, for instance, due to the example I showed before, this would not hold. And in connection with agree, we can make a useful observation. I mean, in agree, the TL is fixed to be the classifier. And so this, just by the property of the partial map classifier, this tells us that for any match M, there is a unique alpha that establishes a strong match, namely the classifying arrow. And because we're just doing pullbacks and pushouts, which are unique up to isomorphism, this means that M fully determines the result of the rewrite step up to isomorphism. So it's a natural question in the PPO plus setting, if you want to be a responsible person, which classifiers can you use? And in many of the examples, also in this spectrograph rewriting paper, for instance, which is like a precursor to PPO plus, we often just use sub-objects of TL. So you just throw out some of the type edges to get a restricted classifier. And it's quite easy to show then that this object here inherits the uniqueness property of the classifier. You just don't know if this, if such an adherence will exist, which is of course what you want if you want to restrict the matching mechanism. All right, then for the last modeling result, we want to model DPO. And I don't think I have to explain to my audience what a DPO rewrite rule is, but I'm just putting this here for to be proper. And note that in particular, the L must be a regular mono for us, which so in particular we cannot do a nonlinear double push-out rewriting, which Bear and others, for instance, investigated last year for an ICGT paper. And what is now then the PBPO plus rule that models this DPO rule? Well, take this only works, I mean, this works in a quasitopos, this doesn't work in any category. In a quasitopos, we know we have this injection into the classifying object. We know that we have pushouts along regular monos, so we can make this pushout here. By stability, we know that these two arrows are regular. And because pushouts along regular monos are pullbacks, we know that this is in fact a pullback and thus a PBPO plus rule. I can give you the proof sketch. It's not extremely hard to follow. Let's say we are given a DPO rule as depicted with some match M. First of all, pushouts along regular monos are pullback, so we know this is a pullback square. And secondly, regular monos in a quasitopos are stable under pushout and pullback, so we know that these two arrows are regular monos. Now, in this picture, we can add in the interpreted rule as follows. Recall that this is also push-out. Then, like I said before, we can also just classify regular monos. We can obtain some classifying arrow here that makes this triangle a pullback. And from the push-out property here, we can get the alpha from the push-out property to make these two parts commute. And from the do of the pullback lemma, the outer part is a push-out, this is a push-out, and so this square here is a push-out. And moreover, it is a push-out along a regular mono, and so it is a pullback. So this part explains why we want L to be a regular mono. Because if GL is not a regular mono, I don't think we are able to show that this is a pullback. And for the last part, then we need to show that this is indeed a strong match, so that this commuting triangle is a pullback. And for that, we can fold this diagram into this cube. And then this triangle is this front face over here. Excuse me. We have a push out on the bottom along a regular mono, and if you check all the faces and notice that all the verticals are regular monos by additivity, it follows that this face is indeed a pullback. Then for the other way around, so we're giving a PBPO plus step, and in principle we just know that this triangle commutes. But you can show that for any PBPO plus step, even if you generalize this tk to arbitrary k prime, you can show that it is a pullback. So in this case, this u prime will in fact be the classifying arrow. And then, we need to show that this square is a push out. If you turn it into a cube again, but we have to rotate it, because note that what before were the vertical arrows, these regular monos are now horizontal. On the bottom, on the top, we have exactly this square that we want to show as a push out. And on the bottom, we have a push out, and all around we have pullbacks. And so by RM quasi-additivity, we can conclude that this top is a push out. That completes the proof. So note in particular that we can use the same matches as well in both formalisms. Okay, so I'm at the conclusion. Still have some minutes. Now, this is just a statement again. And I would just want to close with some concluding thoughts, also to maybe give some material for the discussion. A question might be, where is SqPO in this picture, single push-out? Our conjecture is based on intuition. If we have some partial map from L to R, and we represent it as a span, that this is the rule that will model it. So for the L, we have just this injection into the classifier, so there are no application conditions in that sense, no gluing condition. And then over here, we just specify that we keep only those connections that are attached to the context. Now, why did we, for technical reasons, we didn't include it in the picture, because I mostly know SqPO for these categories of algebras of some unary signature, which I think correspond to toposes. But then in the literature, I know SqPO has also been studied in more general settings, for which I don't know the details very well. And there's one more complication, which is that how I've often seen defined is, if you're in a category C and you want to apply single push-out rewriting, you actually switch to a category where you use partial morphisms. But our thought is that since in the quasitopos these partial morphisms are represented, this should work out in some way. And we know that in the SqPO paper for the categorical setting that I just described, this modeling result is known. But what about if we just talk about quasitoposes in general? Can we say that something like this still holds? We would be happy to have your input on that. Another question that could be interesting is, I mean, we saw a sufficient condition for to get determinism for PBPO plus rewriting in a quasitopos setting. But maybe there are other interesting sufficient conditions. For instance, we conjectured that for this fuzzy graph setting, if you start out by deleting some of these type edges and you get to an L prime, we think we could also extend this L prime by some monic AP, so not necessarily an isomorphism, and this would correspond to like increasing the labels on this L prime, and we think it would still have determinism. And of course, when you're in the other class of categories, a similar question might pop up: what's permitted to ensure we still have determinism? So that could be interesting to explore. And then a last very general question is, to what extent can this result help in unifying meta theory methods, tools? For instance, in connection to that, Jörg and I have some work in progress on a termination method for PBPO plus rules in what we think, based on the assumptions you'll need, will be quasi-adhesive categories. So if that works out, then immediately we have a method for all of these formalisms if we are in a setting of a quasi-adhesive quasitopos, because then we can do the encoding. And beyond that, I've not made a start on that yet, but I'm interested also in formalizing just these proofs and maybe looking at some modeling examples. For instance, in the PGR paper, we were modeling distributed algorithms, and because this is quite powerful, we would be interested in investigating to what extent this can be used there as well. One thing left for me to say, which is thank you for listening, and I'm looking forward to the discussion and your feedback and questions.
Thank you very much, Roy. Thanks for the very interesting presentation. Is there any question or remarks from the audience? So, Nick, please.
Thanks a lot, Roy. Very interesting talk, and nice to see that quasitoposes are so useful.
Thank you.
I was just pretty curious about this part about DPO, because you had a nice slide about where exactly you need special assumptions to get to DPO. I mean, you said you do need the rules to be left linear, but I'm wondering what would happen if one relaxes this. I mean, so where does it go wrong? I mean,
so if the L is not a regular mono?
Yes.
So we would like to arrive at GL being a regular mono, so that when we have that this square is a push-out, we can conclude that it is a pullback.
All right.
And I think, we try to see if we can arrive at it differently, but I think
because you can show that it's, obviously you can show it's a push-out, but okay. Yeah, because I mean, it's interesting. I think this is, we might need to compare notes, because I mean, we then, if you do nonlinear DPO, that's where these multi-push-out complements come in. I wonder what's, I mean, I have this vague feeling that presumably one can come up with slightly more general semantics in PBPO plus.
Yeah,
it should be, I somehow have a weird feeling it should be possible to do nonlinear DPO. And something's very, because I mean, we use a very similar type of construction to get these multi-push-out complements in the first place. Yeah, okay, so we should, but that's maybe a very technical discussion. So
but I think if you have nonlinear DPO, it's often non-deterministic, right? But we do know.
Yeah, so that's exactly the point. So we want to be able to cover these formalisms, and then presumably it'll require some sort of generalization of your PBPO. Pardon.
By taking some other kind of classifier here, maybe.
Exactly. Yeah.
It's
exactly.
interesting.
Yeah. Anyways, thanks a lot.
Thank you.
Barbara has a question.
Okay, so first, thanks for the interesting talk. It's nice to see that all these rewriting frameworks can be encoded into the general PBO plus. I have a question. Of course, the more general you are, the harder it is usually to analyze your rules. And I think my question refers a bit to the very last box that you had on your last slide about the analysis. I mean, I have to admit also I lost a bit of track of the status of the various approaches. Of course, in DPO, we have lots of analysis technique. There is confluence, you can check for confluence result. There's critical pair analysis. There's also support for termination analysis. There are other verification techniques. And then, of course, if you go to this more general setting, you are, of course, in danger of losing some results. But you said that you actually are working on termination analysis, and maybe you can say a bit about the state of the art and what you expect as results in terms of analysis. What do you think is possible in PBO plus?
Yeah, it's a very good question, and indeed, I think you're right that if you do this generally, you lose a lot. We've almost carried through the proof, so we're quite sure that it does work for quasi-adhesive categories. I mean, the main things we just have to show is that we can carry things across the diagram and that we can do the analysis of the step based on the analysis of the rule, and this seems to be the assumption we need. In terms of how powerful it is in the actual things you can prove terminating, we are aware of your paper as well, I think, with Hans Santema also and Sander Brugink. We have not yet compared how they would relate in terms of how powerful they are. So at this moment, I cannot say too much about that, I'm afraid.
I mean, of course, you always only have sufficient conditions, and then you don't know what you can do with it. I mean, in terminal writing, people are quite advanced, and they have a lot of tools. In graph writing, I think a bit less so. Mm-hmm. I think there's probably still work that can be done. And but you say you have a condition that guarantees termination, and then you have to check how many instances you can actually handle with it.
I mean, the idea is that we use a kind of tiling of the right hand side and the left hand side. So by going with regular monos into your graphs, and then we assign weight to those tiles, and see if we can construct, if we can show that always this weight is decreasing. I don't dare, maybe Jörg has some comment on that if he's in the chat now, but I don't dare say exactly how expressive it will turn out.
Okay, thank you.
Thank you.
Okay, any other questions? Well, I have a few remarks, but not really, I don't know, not really. First of all, I have to apologize. Nicholas at the beginning said that this acronym is badly readable, PBPO plus, but it's not Roy's and your responsibility. This is our responsibility because we didn't find a better acronym of this pullback-pushout approach.
I think it's nicely descriptive, at least.
Yes, it's very descriptive. More than agree, but agree was nicer as an acronym. And clearly they inherited this problem. Now I found very interesting the very reasonable restriction of the match to strict morphism. And this is something that actually, I must admit, we missed in our presentation, in our attempt at the time for the pullback-pushout approach was to simplify agree. To simplify agree because agree was powerful, but in a sense a bit too far constrained and too complex to present. And presenting the rules just as a push-out and the pullback looked easier. And we didn't think to this problem about matches, and agree that the restriction to strict matches is very, very reasonable. And considering, and then the generalization from adhesive to quasi-adhesive is a very natural generalization, very, very powerful indeed. unary algebras by Michel Leuve corresponding indeed to preshiftoposes, right?
Yeah.
These are preshiftoposes, and yes, I expect that some encoding, reasonable encoding of SqPO can be done along the lines that you proposed.
Okay, that's nice.
This category of fuzzy graphs. So the category of graphs labeled on these with nodes labeled on these lattices. So the idea is that you still have the idea that nodes belong to the graph with a certain amount of uncertainty.
Excuse me, I didn't catch the part about the idea of the nodes.
Yes, in the fuzzy graph, fuzzy graph that you mentioned at the beginning, you have that the graph is labeled over L, right?
Yeah.
Which is a complete lattice, probably distributive lattice.
Mm-hmm.
And you label both nodes and edges, or just nodes?
So in the conference paper, we label both of them from the lattice. As far as this result by Aloïs is concerned, maybe Aloïs can comment on that, because I think he's still investigating that a little bit.
About what do we label exactly?
Yeah, and if the nodes and the edges come from the same L.
So we allow both sets to have different that edges and vertices can have different labels if needed, if wanted.
Okay.
But in practice, sometimes you want to label with the same set or simply just not label one.
Okay, and the idea is still to see nodes as belonging to a certain degree to the graph, like in fuzzy sets. So the intuition is more or less the same.
Good question. It's true that for fuzzy sets, the map into this lattice represent membership. That wasn't the approach in this case. The desire to have a lattice structure on the labeling set was nice observation by Roy and Jörg about labeling, relabeling using PBPO plus. So I don't know if there is something to get out of it with thinking of this labeling as membership. Maybe, but that wasn't the original approach.
Yeah.
Okay, for relabeling, yes, this is clear. There were some old approaches on the DPO applied to label the graphs where they used to have some partial order on the labels, because it's allowed to also to compose labels in a universal way, basically, in a sense. So to extend the limits and co-limits to labels. I see this is the main motivation, I understand.
We have a comparison with that in the paper as well, in the discussion.
Okay.
If you're interested.
Okay, thank you very much.
Thank you.
Okay. Are there any comments, any other questions? Otherwise, Nick, maybe we could stop the streaming and to see if we to move to a more informal discussion. You certainly had some discussed.
So thanks a lot, Andrea, for being our host today, and of course to Roy for excellent talk. I see there's still some people on YouTube, so if you want to join us here on Zoom, you can still do that for, let's say, I don't know, next 20 minutes or so. You can find the registration link on our homepage. And for now, I'll close the session. I just would like to advertise the next talk, which is going to be on contextual hyper-edge replacement grammars in 2 weeks, I think. Is that correct? Yes, on June 3. And thanks everyone for being here. And you can remain, of course, in the Zoom, but I'll